Most of us are familiar with the surface level effects, the warmth after the first sip, the laughter that comes a bit easier, and eventually the stumbling gait or slurred speech. But beneath that social facade, alcohol is executing a highly complex chemical hijacking. It is not merely a depressant in the sense that it makes you sad. It is a master disruptor that alters the electrical and chemical communication of almost every corner of your gray matter. To understand the buzz, we must first understand the biological siege alcohol lays upon the central nervous system. Unlike many substances that require specific, localized receptors to enter cells, ethanol, the active ingredient in alcohol, is a tiny, agile molecule that dissolves in both water and fat. This dual solubility is its skeleton key. Most drugs are blocked by the blood-brain barrier, BBB, a semi-permeable border of endothelial cells that protects the brain from toxins. Alcohol, however, slips through this barrier with startling ease. Once inside, it doesn't pick one side. It attacks the delicate balance between excitation and inhibition. Because it can travel anywhere blood flows, it saturates the brain entirely, from the primitive brainstem to the advanced prefrontal cortex. It doesn't just knock on the door, it seeps through the walls of the entire house. The brain operates on a precarious balance between two primary neurotransmitters. Think of your brain as a car traveling down a highway. For a smooth ride, you need a functional gas pedal and a responsive brake. Alcohol effectively slams on the brake while cutting the brake lines of the gas pedal. GABA, gamma-aminobutyric acid, is the primary inhibitory neurotransmitter. Its job is to quiet neural activity, preventing the brain from becoming overstimulated. Under normal conditions, GABA maintains a sense of calm. Alcohol is a GABA agonist. It binds to GABA-A receptors, changing their shape so they stay open longer, allowing more chloride ions to enter the neurons. This hyperpolarizes the cells, making them less likely to fire an electrical signal. The result is the initial stage of intoxication. Muscles relax, social anxiety fades, and a sense of tranquility washes over the user. However, as the dose increases, this brake becomes so heavy that it slows down essential functions like speech, motor coordination, and eventually heart rate. On the flip side is glutamate, the primary excitatory neurotransmitter responsible for firing neurons. It is essential for learning, memory, and cognitive alertness. Alcohol acts as an antagonist to glutamate, specifically targeting the NMDA receptors. By blocking these receptors, alcohol prevents glutamate from doing its job. The gas pedal is effectively stuck in neutral. When you combine an amplified brake, GABA, with a suppressed gas pedal, glutamate, you induce a state of systemic sedation. This is why even a stimulating night out eventually leads to the inevitable wall, the moment when the brain's processing speed drops below the threshold of functional awareness. Even before the sedation sets in, alcohol triggers a surge in the brain's reward circuitry. This is the hook. When alcohol enters the system, it stimulates a rapid release of dopamine in the nucleus accumbens, often called the brain's pleasure center. This is why the first drink feels so good. The brain is evolutionarily hardwired to reward behaviors that it perceives as beneficial for survival, like eating calorie-dense food or social bonding. Alcohol tricks the brain into registering the chemical influx as a survival positive event. This creates a powerful reinforcement loop, the urge to keep the feeling going by ordering a second or third drink. However, this spike is artificial and fleeting. The brain is a master of homeostasis. It always seeks balance. To compensate for this massive artificial dopamine surge, the brain begins to shut down its own natural dopamine production and reduces the number of available receptors. This is the physiological origin of the crash. Once the alcohol clears, you aren't just back to zero. You are in a dopamine deficit, leading to the irritability and low mood that characterizes the day after. One of the first areas of the brain to go offline under the influence is the prefrontal cortex, PFC. This is the most human part of our brain, responsible for executive functions such as judgment and decision-making, impulse control, risk assessment and future planning, socially appropriate behavior, When alcohol numbs the PFC, we experience the famous effect of disinhibition. It is a common misconception that alcohol gives you liquid courage. In reality, it doesn't add anything, it subtracts. It silences the internal monologue, the adult in the room, that evaluates consequences. It mutes the part of your brain that says, you probably shouldn't send that text at 3 a.m., or driving right now is a terrible idea. Without the PFC to filter impulses, the more primitive, emotional parts of the brain, like the amygdala, take the wheel. You are essentially operating a high-speed vehicle with a broken navigation system. The phenomenon of blacking out is often misunderstood as simply passing out or being too tired to remember. In truth, it is a profound chemical failure of the hippocampus. The hippocampus is the region tasked with memory consolidation, the process of turning short-term, working memories into long-term storage. When blood alcohol concentration, BAC, rises rapidly, the neurons in the hippocampus are essentially paralyzed. They stop communicating. During a blackout, the recorder is turned off. The person may appear conscious, they may hold conversations, and they may even perform complex tasks, but the brain is not writing those events to the hard drive. Those memories were quite literally never created. It isn't that you forgot what happened, it's that the data was never saved in the first place. A hangover is far more than just the result of dehydration or the impurities in cheap tequila. It is primarily a mini withdrawal. Because the brain spent hours fighting against the sedative effects of alcohol by trying to ramp up its activity, it is caught off guard when the alcohol leaves the bloodstream. Suddenly, the GABA brakes are gone, but the brain is still pumping out massive amounts of glutamate, the gas pedal, to compensate for the previous suppression. This results in a state of glutamate rebound or hyperexcitability. This chemical imbalance causes photophobia and phonophobia, hypersensitivity to light and sound because the brain cannot filter or dampen sensory input. Anxiety, a state of physiological anxiety caused by an overactive nervous system. Tremors, involuntary shakes as neurons fire erratically. Furthermore, as the liver breaks down alcohol, it produces acetaldehyde. This compound is estimated to be between 10 to 30 times more toxic than alcohol itself. Acetaldehyde triggers widespread inflammation in brain tissue, attacking the protective membranes of neurons and contributing to the brain fog and physical pain associated with the morning after. The brain is plastic, meaning it changes based on use. If alcohol consumption becomes chronic, the brain doesn't just react, it structurally rewires itself to survive in a toxic environment. This is known as neuroadaptation. 1. Cerebral atrophy. Long-term heavy drinking leads to a visible shrinking of the brain. The ventricles, fluid-filled spaces, enlarge to fill the gap left by dying tissue. This shrinkage is most pronounced in the frontal lobes, further eroding the ability to control impulses, creating a vicious cycle of addiction. 2. Oxidative stress and vitamin depletion. Alcohol interferes with the absorption of thiamine, vitamin B1. This can lead to Wernicke-Korsakoff syndrome, a devastating neurological disorder characterized by permanent amnesia and confabulation, where the brain makes up fake memories to fill the gaps of the ones it has lost. 3. Anhedonia, the death of joy. Eventually, the reward system becomes so depleted that normal activities, eating a good meal, enjoying a hobby, or feeling affection, no longer produce pleasure. The brain's pleasure threshold is raised so high that only the massive chemical hit of alcohol can trigger a response. This leaves the individual in a state of chronic emotional numbness when sober. It is vital to note that the human brain does not finish its construction phase until approximately age 25. The last part to wire up is the prefrontal cortex. Introducing a chemical sledgehammer, like alcohol, during this critical developmental window can have permanent consequences. Research shows that heavy drinking in adolescence can permanently alter the formation of white matter, the wiring that connects different brain regions. This can lead to lifelong deficits in cognitive flexibility, emotional regulation, and memory capacity. Essentially, drinking heavily in your teens and early 20s is like trying to build a house while someone is constantly shaking the foundation. Alcohol is, in essence, a promiscuous modulator. It doesn't have a clean, surgical target like many modern medicines. It is a chemical sledgehammer hitting the delicate architecture of your mind. It affects every neurotransmitter system it touches, from the opioids that provide the warmth to the acetylcholine that governs movement. Understanding that the buzz is simply the byproduct of a massive interference in neuronal communication allows us to view consumption through a more conscious lens. The laughter and relaxation come at a metabolic and neurological cost. While the brain is remarkably resilient and capable of significant healing after periods of abstinence, the price of the buzz is often paid in the currency of long-term neurological health and cognitive clarity. The next time you hold a glass, remember, you aren't just drinking a liquid, you are inviting a master disruptor to rewrite the chemistry of who you are, one neuron at a time.